Structural Analysis 2, Chapter 8, Deflections using Energy Method. Let's solve another example like a beam ABC with two support of A and B distributed pounds per feet, and we want to know what is the vertical displacement delta V at C. So if you want to solve this problem, if you want to calculate the vertical displacement of point C delta C at V delta C at V, and while we know I moment of inertia is 100 inch to the force and modulus of elasticity of steel, which is frame of our is 29,000 kilopound square inches. So let's attend our problem with virtual work method. So in this kind of problem, by simply jotting down the equation of 1 times delta CV is equal to applying a 1 kilopounds vertical virtual force, then we can create small m capital M pi dx, and if we integrate it from 0 to L, it just simply gives us what we are looking at, which is the delta at point C vertical. So we have to create the small m and capital M for our figure. So if we cut our beam through a arbitrary distance from A to B, so this is our cross section, definitely you can see can have a moment here which is mx, and definitely we are in the real moment part, so we are in capital M. Why is that? Because we are calculating the structure due to its own real forces, and you can definitely know mx in the part AB, it doesn't remains the same to interference and support B. So if we cut it through here, we have another mx or another mx, or for example you can call it part 1 mx1 and part 2 which is mx2. So definitely for each part we have to calculate the real moment times the virtual one, plus this is for the first part, and then for the second part we also do the real moment, which remains the same with the first part due to the actual loading, plus a virtual one, which is mainly different with, and if you add the superposition and add these two up together, it just gives you 1 times delta C vertically is equal to 0 to L small m capital M EI dx. So now we are going to we are just moving on to create our M capital M, and then as soon as you replace in the equation and integrate it over the span of beam, you can easily get the vertical climbing down of point C in this example. So first of all, if we cut our section through, there is a moment developed here like mx and capital X due to actual load. We are, or for the actual load, we are showing it by y the capital M, and for the virtual one we use the sign of small m. So in that case, if you just cut it through by arbitrary distance, they are through the real forces, because we are just considering the real force on a structure. And if we call it like x or x1, the distance, and if you convert the distributed load to a concentrated load, just gives you the 2 times x1 times x1. Because the intensity is 2, distance is x1, that's 2 times x1, and summation of moment about x goes 0, it just gives us mx, which is positive to our direction, that's positive, plus the force, and it's created. Then minus, there is the 150, there is 1500, at the support. And how you can get the support for this structure? By simply calculating the total load, that's W, which is 2 times 30. It turns like 60 kips, and this 60 is applied something like at the half of the center. So its total is 30, it's just 15, and 15 has a 5 meter from part A, also a different part. So that's easily you can get what RA is, which is I think that's 15, and RB is 45. Definitely B is closer to the support, handling more share of axial force. So as soon as you have the equation for capital M, which remains the same in both structure because that's due to the real forces on the structure and it doesn't change from part A to part B. And again for part A I mean from A to B. Again for virtual work of that we can apply a, because we want to calculate the vertical displacement, so we have to apply a concentrated load equal to P prime equal to 1. So, and then if you cut the section through this time from C, it just gives you, my bad, if I cut the problem from A to B, it just gives you mx, and the summation of moment about x goes 0, summation of moment about x goes 0, and this is x. It just simply gives you mx, small mx plus 0.5, which is the downward reaction at point A, and it just make it like mx plus 0.5x equal to 0. If you do so, it just gives you a small mx of A equal to negative 0.5x. As soon as we have the capital M, real and capital M, small m for the first part of the problem, can jump to the second part to do the same process, and then by the use of superposition, add all of them together to report like one result. So this time, if we just cut the beam through section C to B, definitely this is x2, or you can call it either by x1 and x2, and just remember to not mess with them. Again, we have the same story, and it just gives us a mx equal to a negative x squared to an x2 squared. So as soon as we have this is exactly the same moment we got in the first part. And if now if we just come to the virtual force on the structure, they are just doing different kind of the solution involve applying different methods, but as if you just cut the section through, it just gives you mx equation is equal to mx is negative x. So as soon as we have the virtual and real moment for both parts, just writing down the equation of 1 times delta c vertically is equal to integration all over the span m times capital small m capital x over ei. That's all we need to do. So if you just replaced even the equation of the real moment for the first part, for the second part, again for the second part and for the first time, we just have all of them. So by simply multiply part 1 times the real one times the virtual one plus the real one times the virtual one, another summation, so just gives you this equation down. Just be careful about the limit of your integration. So as soon as you have this equation and write down the equation of 0.10, 0 to 0.20, 0 to 0.20, which is for part AB, and for the other part it's just 10 feet, and let's see how we can solve it. So the first part is small m, capital M for the first part, then Second one, again, this is a small m, capital M. Why is that important? Because for real forces, you can have your chart from previous page to have it like completely just for your verification. As soon as you have that, it just gives you the first equation from 0 to 20 integration. It just cancels out each term and goes 0, and the other one gives us a 500 per EI kilopounds times h square, h cube. It just turns to be delta C vertically is 1.49 inches. Thank you. We'll solve more problems.